So the third skill in this problem is actually thinking about what Ecell is. And to kind of go back to our last problem that we just went through here, we diagrammed a voltaic cell. Well, one thing that we kind of left blank here was we didn't write in what the voltage is for this cell. And that's a quantitative determination of kind of how the electrons are coming through here. What kind of thermodynamic driving force do we have for the electrons to move through here? How spontaneous is this reaction? And we can actually do that quantitatively. So we're going to start here with an in-class problem that kind of goes through with a little bit more detail how to calculate Ecell. We're going to have two examples that we go through. The first one has to do with when you actually know who the anode and cathode components are. And then the second one is, hey, draw me a spontaneous tin-silver voltaic cell. So we actually have to do a little thinking to think about who's going to be in the anode compartment and who will be in the cathode compartment. So again, that's what we have to think about with calculating Ecell. So again, the first part of this is just kind of understanding what E is. And E really just has to do with an electromotive force. It has to do with how spontaneous this redox process is occurring. And remember, for redox processes, somebody has to want to gain electrons and somebody has to want to lose them. And the greater that difference is between somebody wanting to give up and somebody wanting to gain, the greater the spontaneity is for that process. So one of the things that you have to make sure you remember, and it was a little bit different in Chapter 20, for a spontaneous process, we want a large positive E value. Remember, for delta G, spontaneous reactions are large negative delta Gs. So it's a large positive E value when we're doing electrochemistry. So we have some steps here to think about in terms of calculating Ecell values. They're on this sheet here, so we'll kind of walk through them as we work through these two in-class problems. Okay, so the first step is to write half reactions occurring. So for our first problem here, we have our typical zinc copper galvanic cell that we've looked at for some time here in lecture. So we have to write half reactions that are occurring. And again, for some problems, we already know who's being oxidized and who's being reduced. And for this zinc copper half cell, we do, right? Because we know that our anode is over here and our cathode is here. And we know that oxidation, anox, occurs in our anode compartment, and then reduction occurs in our cathode compartment, red cat. And again, if we need to remember, you've got negatives and positives that we can put in here. But this gets us good enough now. We know that our anode compartment contains our zinc electrode and our zinc ions. And so if we consider oxidation, we're going to have zinc going to zinc 2+ plus 2 electrons. So that's our oxidation half reaction. Our reduction half reaction occurs when copper ions gain 2 electrons. And again, those 2 electrons coming through the wire that zinc has given up, going over to the cathode, pulling a copper ion out of solution, and plating out copper solid on this electrode. So here are the two half reactions. And what we do now is we need to look at Appendix D. So we wrote the half reactions occurring, and again, we knew who was being oxidized and who was being reduced. As we'll see in our next problem here, if we don't know who's being oxidized and who's being reduced, we'll write them both as reduction half reactions, and then we'll work out how to figure out which is which. So the second step is to find the E values on Appendix D. Okay, so we need to make sure we're looking at Appendix D here. So here's our Appendix D. We need to look them up for zinc, and we need to look them up for copper. And make sure here, there's 2 copper ones here. This is copper 2+ going to copper plus. We don't want that one. In this case, we want copper going to copper solid. And then here's zinc. So what we're going to do now, and this is again where my strategy is a little bit different from what your book does and from what you may have already learned. Whatever works for you, as long as you get the right answer, that's fine. I'm going to be consistent with this strategy. I'm going to write an E0 value. But because I know that this is an oxidation reaction, I'm going to write OX. Okay? This is a reduction reaction, so I'm going to write E0 RED. And up in our directions here, it says for reduction reactions, use the value on the table, write as E0 reduction. For oxidation reactions, use the negative of the value. And again, I'm going to remind myself that I want the negative of the value because I write EOX. And again, we know who's oxidized and who's reduced in this chemistry, so we can go ahead and do that. So if I look up the value for zinc here on this table, the value for zinc here is negative 0.76. But because I want this as an oxidation reaction, I'm going to flip this. So it's positive 0.76 volts. The reduction reaction for copper, again, I can look up this directly. Copper here is 0.34, and it's positive. So that's how we completed step 2. Step 3, scale the equation if we needed so that the electrons lost equals the electrons gained. In this case, no scaling is necessary. Our oxidation provides 2 electrons. Our reduction needs 2 electrons. If you needed to scale these equations so that the coefficients allow us to have electrons gained equals electrons lost, you do not scale these values. And that's really, really important to understand. We don't scale those values. We'll see in our example down here where we'll have electrons lost not equaling electrons gained, and we will need to do some scaling, but you never scale these values, okay? Don't need to do any scaling, so step 3 doesn't apply to this first problem. Step 4, we need to sum the equations, and again, our electrons should cancel, and then also sum the E naught values. So E cell equals the reduction plus the oxidation potentials. A spontaneous reaction will have a positive E cell. And again, if you don't know which is oxidation or reduction, and we'll see that down here, we're going to flip and reverse the sign of the reaction so that we can have a positive E cell. All right, so if we go ahead here and we sum these up, we're going to add our phases back in. So zinc solid plus copper ions gives us zinc ions in solution and solid copper. E cell then is going to be equal to 1.10 volts. And again, because this is positive, that means this is a spontaneous process. Well, we already knew that this was a spontaneous galvanic cell as written, where zinc is going to be the anode, copper is going to be the cathode, and that's going to generate a voltage of 1.10 volts. So what we're going to move on to now is our second problem here, where we're going to have tin and silver. And we don't know who's going to be the spontaneous reaction in terms of who's going to be the anode and who's going to be the cathode. So we're going to have to do some sleuthing to figure that out. So you got to remember that tin is Sn and that silver is Ag, or else you're going to have a really hard time when you're looking things up by their atomic symbol here on Appendix D. So again, we're going to write the half reactions, and because we don't know who's going to be oxidized and who's going to be reduced, we're going to write them both as reduction half reactions. So in this case, tin, it's going to be tin 2 plus. It's going to gain 2 electrons and become solid tin. Silver cations are +1 charged. So as a reduction reaction, we'll gain 1 electron and become silver solid. If we go ahead again, and I'm not going to go through the details of this, we can look up these values on our table here. As reduction reactions, we're going to get this as negative 0.4 and this as positive 0.8. Now we know we need to flip one of these because one of these has to be an oxidation. And remember, when we flip it, we're going to have the negative of the sign. So hopefully it makes sense that if this is the reaction that we'd flip, we'd add negative 0.14 and negative 0.8, and we would not have a positive E cell in that case. So hopefully it's pretty straightforward to realize that this is the guy that we need to flip. So we're going to flip this reaction. So again, this guy is going to stay our reduction. This guy we're going to flip. Oops. This is going to be our oxidation. So I'm going to write E ox here to remind me that this is going to be one that I'm going to flip. Positive 0.14 volts. Okay. Now, we're not going to be using this one anymore. We needed it as an oxidation. So we need to sum these two, and we need to realize that this guy needs to be scaled. So we need to scale that one. So again, we need to scale it by 2-fold. So I'm just going to rewrite this so we have this here. 2 silver ions plus 2 electrons goes to 2 Ag. Now, we are still going to maintain the same value here. We do not scale that value. sum these up here. Solid tin plus silver ions generates tin ions plus solid silver. E cell for this process is going to be equal to positive 0.94 volts. Now, if we had switched this around, we'd end up with a value that's negative 0.94. And again, that wouldn't make any sense. That would not be a spontaneous process. The last thing I want to do was take this and kind of map it onto a voltaic cell here. So oxidation, right? Oxidation here is with our tin. Oxidation occurs in the anode. So again, anode is always by convention on the left, cathode on the right. So anode is where oxidation occurs. Oxidation again was our tin process. So this is going to be a tin electrode, and we're going to have tin ions in solution. So our reduction compartment, our cathode compartment, is going to have silver ions in solution, and then a silver electrode. Anions, again, are going to flow over to our tin compartment because we are going to be generating those tin ions, so we need to neutralize them. Cations flowing over to the right. And now we can fill in this box here. This is going to be 0.94 volts as electrons move through this voltaic cell.